Good morning and welcome to today's UCIe Consortium webinar introducing the UCIe 3.0 Specification, Continued Innovations in the Open Chiplet Ecosystem. This morning we'll be hearing from our presenter, Dr. Debendra Das Sharma, who is a Senior Fellow and Co-GM of Memory and I/O Technologies at Intel Corporation, as well as the UCIe Consortium Chairman. I'll turn it over to you now here, Debendra.
All right. Thank you, Samantha. Hey, greetings, everybody. I'm really excited to talk about the third generation of Universal Chiplet Interconnect Express, abbreviated as UCIe. This is the disclaimer that you can all read through. Now, here is the agenda for today. We'll start off by introducing UCIe, then provide an overview of the past three specifications, UCIe 1.0, 1.1, 2.0, and then delve into the 3.0 enhancements, which are for planar interconnects, namely UCIe-S for standard and UCIe-A for advanced. These are things like improving bandwidth density. We are double the data rate to 64 gig. We are adding support for a new usage model. We'll talk about that, continuous transmission protocols. Then we'll talk about some of the power savings enhancements we have done, both for operational power savings as well as idle power savings, and then talk about a set of manageability enhancements that we have provided for seamless interoperability, things like firmware download, sideband, star topology, open drain, fast throttle shutdown, all of those. We are going to do a deep dive into the key metrics with UCIe 3.0, talk about future directions and conclusions. And at the end of it, we will have the question and answer session. We'll do a block with the question and answer session, including any questions that we could not get to today. UCIe, it's an open standard for chiplet development. Our guiding principles has been, of course, it's an open ecosystem. We believe in backward compatible evolution to ensure that investments are protected. Of course, we will continue to deliver the best power, performance, and cost metrics across the entire compute continuum, right? Not for a segment, but for the entire compute continuum. And continuously, we are cognizant that we need to continuously innovate in order to meet the needs of the evolving ecosystem. And several of us that are in the standard have had decades of experience driving very successful industry standards at the board level, PCI Express, CXL, USB, all of those. So, all of these basically guide us in the journey with UCIe. So high bandwidth, low latency, cost-effective, power-efficient interconnect, and that spans across the whole compute continuum, whether it is handheld, AI applications, edge, HPC, cloud, enterprise, 5G, automotive, you name it, right? So that's basically where UCIe is targeting the entire compute continuum. UCIe has got 140 plus member companies and it is growing. The list of the board member companies is provided here. And if you look into the companies, these are the who's who in the fields of IP suppliers, semiconductors, packaging technologies, foundries, cloud service providers, automotive, the entire gamut. As always, we are open for membership. So if your organization has not joined, consider joining us either at the contributor or at the adopter level. And that depends on what you want to do. Both contributor and adopter, they get access to the specifications along with all the IP protections and all of that. Contributors just participate in the development of the specification as it is going through. So whatever is appropriate for your organization, you can decide to join UCIe Consortium if you have not done so. We are, a membership-driven organization, and we drive the specifications by the member companies, basically bringing in their requirements, and then we do the specifications based on that, right? So this is a brief history. March 2022, we formed the consortium with 1.0 specification being released. Then in June, we incorporated the same year. 1.1 specification was in August of 2023. It had effectively enhancements for automotive segment and some enhancements for compliance testing. UCIe 2.0 was released last year. We'll talk about that. And UCIe 3.0, which we are going to talk in a lot of detail, was released a couple of months back, less than a couple of months back. So we'll talk about that in a lot more detail. These are the work groups for the consortium. There are five, work groups: electrical protocol, form factor compliance, manageability, security, systems, and software. So these are the five technical work groups. Now there are two work groups that are what we call horizontal. That's the automotive that gathers the requirements and feeds into these working groups, and then the marketing working group. So let's do a quick overview of the UCIe 1.0, 1.1, and 2.0 specifications. There are many drivers for on-package chiplets. As the die size increases, we need to meet the growing performance demand. So a lot of the designs are coming up against the reticle limit. And this is rampant across the volume segment, whether it is multi-core CPUs, GPUs, everybody has the same challenges. Second challenge is yield. Larger dies have challenges with the yield. Smaller chips, of course, they yield better. Third one is around on-package memory. We need to deliver high memory bandwidth to feed the processing capabilities that we are developing. And then there are other emerging drivers like IP porting costs. These are exploding with the advanced process nodes. So it makes sense to reuse chiplets whose functionality does not change. Cost in the advanced process nodes is high, so it makes sense to only put those functions that benefit the most from the most advanced process nodes, like compute chiplets. Other functionality, whether it is a memory controller, I/O controller, that can be in a mature process node, and you can reuse the proven chiplets. Chiplets, of course, offer time to market advantages because you are reusing the proven chiplets. You are not redoing them, moving everything to a new process technology, a large chip. And you can offer custom solution depending on the chiplet. Now, if you look into this picture over here, you have you can come up with your mix and match of different types of compute cores in different chiplets, memory, accelerator, I/O, depending on what use case you are trying to satisfy. So bottom line is we need to think of the package as an open innovation slot with UCIe. This is just like PCI Express, for example, at the board level. With UCIe, the SIP or the system in package is the SoC, and also the SIP is the platform of innovation. Now let's do a brief overview of the first generation of UCIe, that is UCIe 1.0 and UCIe 1.1. These are planar interconnects, and you can get the details of those. There are some white papers listed here and some webinars listed here. You can go through those and get much more details. Physical layer, as you can see on the picture in the right here, it includes things like your clocking, analog, channel, sideband, scrambling, descrambling, bump map, link training, lane repair, lane reversal, the whole 9 yards there. On top of the physical layer, you have the die-to-die adapter. It handles reliable delivery of the bits. It has things like CRC, read-try, and it can support multiple protocols by dynamically multiplexing between them if that's needed. Protocol layer can be PCI Express, can be CXL, can be any proprietary protocol, can be any streaming protocol. Now, why CXL and PCIe? Well, these are the ubiquitous standards. A lot of the SoC construction issues are addressed since PCIe or CXL are widely deployed at the board level. People just need things like a clock and power they know how to make things work with the existing design. So things like device discovery in software or error reporting, these are all well taken care of by existing software infrastructure. Now, from a usage model point of view, you also have huge coverage, like you can address I/O attach with PCI Express or CXL.io. You can do the memory use cases with CXL.mem, and you can do accelerator use cases with a combination of CXL.io, CXL.mem, CXL-CAS. And in addition to that, you can do streaming protocols, things like CHI or any other SMP cache coherency protocol that you can run on top of the UCIe stack. And this is similar to a lot of the SMP cache coherency protocols they run today on PCI Express 5. We also define things like the configuration registers, your manageability, security, form factor, compliance, internal IP interfaces like the ones that we show over here and here for plug and play. These are all essential ingredients for a successful ecosystem. UCIe supports both standard package, that's oops, I moved. Okay. Standard package that's shown here, and then the advanced packages that are shown over here. Standard package is called 2D. It's for cost-effective systems. The distance is 25 millimeter on package. Your bump pitches are 100 to 130 micron. Advanced package is for power efficient performance and very high density. Your bump pitches range is 25 micron through 55 micron. And the distance between the dies or the micro bumps here is less than 2 millimeter. Now, there are multiple options available for advanced. As you can see, we have given 3 examples here. This is Intel CMIP, TSMC Scovers, and AS's Focus, and there are many, many more examples of that. The promise of UCIe is that the dies can be manufactured anywhere and they can be assembled anywhere, and you can do the mix and match. There are a couple of webinars that we have listed here at the bottom if you want to get more information about these aspects here. With UCIe 1.0 and 1.1, like we said, we address the planar connectivity. Now, with UCIe 2.0, we introduced the notion of vertical chiplets called UCIe 3D. There are a rich set of technology choices available for vertical chiplets. They have been used by memory device manufacturers for more than a decade. They have also been used by computing devices in some of the recent products. One of the key trends for that 3D technology is something like hybrid bonding. And these are basically, they rely on very aggressive shrinking on the bump pitches between the chiplets. And you're looking at bump pitch between starting at 9 micron, going down to submicron. With hybrid bonding, you reduce the interconnect distance between the chiplets to practically 0. So what that means is that your interoperability now needs to be constrained to the same bump pitch. For example, if chiplet 0 in this picture and chiplet 1, you need to put them together. Both need to have the same bump map and the same bump pitch so that you can fuse them. So if this one has got 3 micron, this has to be also 3 micron and the same bump map, right? So that's the constraint that you have. But in return, what you get is a tremendous benefit in the KPI improvements that we will see. So let's talk qualitatively a little bit about those KPI improvement. First is the increased bandwidth density. We get a twofold benefit here. Like I said, the bump pitches are shrinking aggressively for the vertical chiplets, 9 micron down to submicron. So what that means is that the number of wires that you get for a given area, it increases inversely as the square of the bump pitch distance. Let me give an example. If you consider a bump pitch of 25 micron versus another implementation whose bump pitch is 5 micron, there is a 5x decrease in the bump pitch. But the number of wires, because of the 5x decrease in bump pitch, goes up by 25x. That's what happens, right? And if that 5 micron goes down to 1 micron, then you get another 25x increase in the number of wires, right? So that's a tremendous increase in the number of wires. The second aspect is the area itself. With 3D, you don't have to go to the edge of the die to route the wires. You can connect them in place like is shown here. So you basically get the entire surface area of the chiplet to connect to the other chiplet. So that gives you a lot of area to make your connection. So practically, you're not wasting any area on the die. This picture that on the top shows 2 chiplets with 9 NOCs that are connecting to the 9 sets of PHY, as you can see here. So the NOC connects directly to the PHY, and then the chiplets are connected there. Now, with all of these, what we really need to do is make the associated circuit simple so that we continue to be bump limited, right? And that's the critical part. You need to be bump limited. That way you're going to get the benefit of the bump pitches. If your circuit area is larger than the bump area, then you didn't get the benefit of the bump pitch reduction. It is going to be the least common denominator between the two. Now, with the orders of magnitude improvement in wire density, that we get, we can take a completely different approach with 3D, which is what we did. Basically, we went with simple circuits, reduced frequency, so that we get even lower power. And as you will see that we get an order of magnitude improvement in the power. And then at the same time, because of the square nature of the number of wires that we have, we get tremendous improvement in the bandwidth. So we are getting benefit from both the sides. So as a result, what happens is 3D interconnected chiplets with their low bump pitches, they offer better latency, better power characteristics than even large monolithic dies. There are some resources that we have listed here at the bottom that you can take a look at for doing a deeper dive into UCIe 2.0. Now with UCIe 2.0, we addressed the many challenges to realize the vision of an open plug-and-play chiplet-based ecosystem. There are few aspects: testability, manageability, debug. These needs to be addressed at the SIP level and even at the platform level. So let me explain. With UCIe 1.0 and 1.1, we addressed these aspects at the interconnect level. We had things like loopback, we had things like margining, fault reporting, sideband, all of that. With 2.0, what we did was we took a step ahead and we addressed them at the SIP level. And we didn't say that, hey, UCIe is about an interconnect, so we just deal with things at this interconnect level. We are dealing with things at the entire package and at the entire platform level. And of course, for that, we need to make sure that we work collaboratively with other existing standards. And let me talk about that in a bit here. So our approach was we need to think about these things holistically. For example, what happens from the die sort to the package bond to the field level, all aspects of the entire silicon life cycle that we need to deal with. Now let's take an example of testing, right? If you want to test with an AT tester, you can probe bumps, and that's fine. That's a well-known technique. But you can't probe micro bumps, especially when the bump pitch goes towards 25 micron or even 9 micron down with the UCIe 3D. So, we had to be innovative and use other bumps. As you can see in the table here, these are some of the other bumps that we use. The UCIe standard, you can do PCIe, you can do USB, and so on and so forth. You can use that and then use that to launch your test vectors and test the UCIe infrastructure along with, of course, the rest of the chiplet. Similarly, when we look into things like repair at the assembly and in the field level, how do we deal with that? How do we deal with loading firmware or making firmware upgrades when something has already been deployed? How do we debug, for example, right? I cannot put a logic analyzer in this UCIe link here. Once I have packaged and take a look at the signal, I can put a scope, right? All of these things. How do we do manageability? How do we do these things securely, right? So, and then the other thing that makes it interesting is that how do we address these aspects when even some of the chiplets may or may not be directly connected to an external package pin? Like you can see here, some of these chiplets are not connected directly to external package pin. So that's the thing. And then the other thing is that we also, different chiplets have a wide range of bandwidth demands for these aspects, right? So you have a wide range of scan chain bandwidth demand depending on what chiplet it is, a wide range of bandwidth debug bandwidth demand, right, at runtime. So the table here that we provide, it lists some of the bandwidths that are available, and these are there to satisfy that demand. So you can do things in a scalable manner, not just inside the package using UCIe, but also how do you deal with the interface outside of the package at the platform level. So with UCIe 2.0, we introduced another thing, a sideband only interface for doing explicitly testability, manageability, debug. That is with UCIe-S, and with that you get 800 megabits per second bandwidth per direction. We also introduced the notion of a native by 8 UCIe-S if you need more bandwidth. So these are dedicated bumps for test, debugability, manageability, so that way you can use them if you didn't want these aspects to be interfering with your regular traffic. Of course, you have the option of time multiplexing with your existing UCIe links. So what UCIe 2.0 did was it defined a common management fabric comprising of management ports. Even though we call it management ports, those can be used for testability, manageability, debug. So that comes under a common umbrella, common elements, a director chiplet that can communicate through packets. And we also defined a common software infrastructure by leveraging existing industry standards like MCTP. And we talked about how we support a wide range of bandwidth needs. So a common UCIe test debug management infrastructure was basically what we contributed with UCIe 2.0 in order to make these things seamless. Now let's talk about the UCIe 3.0. Let's delve deeper into that, and we'll start with the doubling of the bandwidth for the planar UCIe, that is UCIe-S and UCIe-A. The UCIe 3D will continue to be at the SoC frequency only at less than 4 gig that we will see. So there is an insatiable demand for high bandwidth in applications like AI, HPC, data analytics, and the SOAR line, it continues to be constant, right? My die sizes are growing bandwidth demand is to double the frequency as long as we are, again, bump limited and our power consumption is constrained, right? And the other way is, of course, to reduce the bump pitches like we talked about. So UCIe 3.0 addresses this demand by increasing the maximum data rate from 32 gig to 64 gig, and we also have 48 gig support in between. We achieve this increase in data rate while maintaining full backward compatibility, right? That's the part you will see over and over. I'll stress full backward compatibility with previous versions of the specification. It's a critical consideration for us as it ensures that existing systems, existing infrastructure, they can seamlessly integrate with the new standard. And it provides a smooth transition path for system designers and developers. And also it ensures interoperability with older chiplets that are designed to the prior generations of the specifications, and they might have their own cadence of making the changes, right, to their interfaces. So as a result, we made no changes to sideband, valid, track, data, training, signaling protocol, bump map, those sets of things. The technical approach to achieving these higher data rates are we continue with the NRZ signaling. This is the non-return to zero unidirectional signaling. This is a proven technique that offers very robust signal integrity, and it is consistent with the prior versions of the specification. Additionally, we also say that the existing quarter rate clocking that existed for 32 gig and lower data rates like 24, 32, it extends to 48 and 64. Bit error rate is 10 to the power minus 15 for 48 gig, 10 to the power minus 12 for 64 gig. And this ensures that your data transmission remains reliable by using your existing CRC and replay mechanisms from the prior generations of the specification. So even at this increased speed, we are going to still use those. And even though we reduced the bit error rate to 64 gig, we had a lot of headroom and our fit was 10 to the power minus 10. So a 3 order of magnitude reduction in the BER doesn't make a dent. We'll deploy enhanced equalization techniques to support the increased data rates. These are things like having a 3-tap transmitter feed forward equalizer, FFE, and that provides precise control over signal shaping. It minimizes the intersymbol interference. We also have a first order passive receiver side continuous time linear equalizer, CTLE, that optimizes the signal quality by compensating for any channel impairments that are there. We also have the provision for an optional one-tap receiver side decision feedback equalizer, DFE, that if you need additional signal conditioning. And we'll see in the next slide, we made some enhancements to the existing link training state machine to perform these IO optimizations and equalization preset selection to establish the desired I margins. And with all of these changes, we see that we have here, the doubling of the data rate bandwidth density happens while keeping power efficiency about flat that we will see later. Now, this table is a summary of the clocking strategy. So 48, as I said before, 48, 64 gig, they mandate quarter rate clock, valid framing, and fast idle entry exit through the valid gating remains the same in order to save power dynamically, but the clock needs to be free running. This shows the training and equalization at 48 gig and 64 gig. The IO training, it's done in this RX calc state, and this is where you adjust the preset values. So if you need more time to do your equalization, then you can always take the arc back from this state to the data train state, and then come back and pick up from where you left in terms of the equalization setting, if that's what is needed. And there are 6 sets of presets that are listed here along with the coefficients. So you pick whatever works the best for getting your RX margin. Also remember I said that we have an RX CTLE. There are 7, I've not shown that here, but there are 7 settings to choose from, -6 dB, -5 dB, all the way down to 0 dB. And you select whatever works the best for your given channel and for your given receiver working with the transmitter. Now let's switch gear and talk about a new usage model, which is the support for the continuous transmission protocol. And the applications are things like a DSP circuit, right? So for example, you have a DSP circuit here, and you're doing all the signal processing, and then you're sending off the bits to this SoC that is over here, right? That's roughly what the idea is. And these kind of applications are characterized by the need for uninterrupted data transmission, and it's needed for maintaining the integrity and accuracy of these tasks. Now, when we discussed this, we looked at it. We said that there is a fixed set of frequency that you will see, right? UCIe has 4, 8. We talked about that. These are the frequencies. But internally, for these analog kind of circuitry, they may not be operating at those discrete points. They might have something like, let's say, I'll pick a number here, 3.9 gigahertz, right, is what they want to operate on. Okay. So in that case, we can always put another PLL, and we can always put a elastic buffer here and then send the signals across. But that causes, these are very sensitive analog circuitry, so it can cause noise in there. So the intent was let the left side work at the frequency that it likes to work. Don't put a need for an additional PLL. Let the data come to the SoC side, and of course, the SoC will process it at whatever internal frequency it processes it by. It is going to have its own, elastic buffer to do the clock domain crossing onto the other side. So, in order to do that, we basically said that there will be this range of frequencies that we will allow, but the setting is still the same, but it can be any frequency between here and here. And the way you get that frequency is by adjusting the ref clock. So that's basically what this particular mechanism is, right, that we talked about. But the compliance is only for the data rate at that is at the links speed setting. So this enables them to get around that issue. Second one is that the specification enables the use of, we had this particular usage required to send things like periodic synchronization marker, like I'm alive kind of a message, or a parity bit periodically. It's not full bandwidth. It's a low frequency kind of a handshake mechanism, if you want to call that. And when we looked into, and of course we could have chosen to add another wire, data wire, but then that would have made that would be a completely different IP, right? It's not going to be backward compatible. So what we did was we looked into the valid signal. For UCIe retimer, we had some additional encodings that we used for doing credit transfer. And in this case, of course, this is not a UCIe retimer. This is this different usage. So we reused some of those encoding for doing synchronization and doing those additional information that you do. So you get about 1 bit for every 80Y. So, and that still is a very high bandwidth to get, given that these operating rates are fairly high. So, and then of course we made all the changes to the RDI and the FDI interface in order to enable this. So small changes that we did enables a whole different class of usage model, which is always a good thing for us to do. As a standard, we want to be more inclusive, as I said before, right? We want to be the ubiquitous standard. So that this is along those lines. Now, let me switch gears again and talk about some of the power efficiency improvements that we have done. Power efficiency improvement is a continuous learning process, and it is essential, of course, in modern computing applications. Our systems are becoming more and more complex as we are getting constrained by the available power. So every means that we can come up with to optimize power consumption is a good thing. So with UCIe 3.0, we introduced an additional power saving feature for the physical layer. Basically, this allows the transmitter adjustment of the clock to data skew during runtime calibration of the link. Now, this capability was previously available only on the receiver side. And we also had it available on the transmitter side, but during initialization. So what we do is that we enable that same flow that we had during initialization during runtime to do it on the transmitter side. Of course, we have the thing on the receiver side also, but transmitter side is also effective. So that way we will result in power savings. Now talking about the idle power savings. So idle power savings are also critical because when your link is not in use, when your components are not in use, you put them into the L2, right? And there your power saving needs to be super low. Prior to 3.0, what would happen in that L2 deep power saving state is that your main band would be completely power gated, completely power gated, and your sideband infrastructure would be clock gated. Okay. And that gets us very good power savings, but of course we want even more. So what we did with 3.0 is we wanted to that sideband, of course we have the option of before 3.0 to just clock gate it, but that sideband we wanted it to be power gated to a large extent. Okay. So what we did was that we utilized the same existing sideband clock and data pin to indicate L2 exit using DC signal levels. And we'll see that in a picture shortly. And of course, with that, a small amount of logic needs to be active to detect the toggle in the sideband clock and data. Other than that, the rest of the sideband logic can be completely power gated, right? So this will result in very aggressive power savings. And we have provided the rules to ensure that it can be symmetric, or it can be even one-sided exit, asymmetric in nature with respect to the L2. So that's what we did. And this is the example. This diagram here explains how that works. Both the chiplets are in the L2 low power state. So sideband clock and sideband data are 0. Now A wants to exit from the L2 state, so it pulls the sideband clock to 1. Now B, of course, has most of the sideband in power gated mode, but the part that is monitoring the sideband clock and data is active. So it detects that, oh, I see this signal became a 1. So it brings up the rest of the sideband, and then whenever it is ready to do the sideband initialization, it indicates that, hey, I'm also ready to wake up by pulling up the sideband clock to a 1. And then about 100 nanoseconds or so later, both sides pull it to 0, and then they are ready to do the link initialization, right? So off they go. So that's what we did. Again, a small change using existing, no new wires, nothing, right? And we just get more power savings. Now, again, switching gears and talking about manageability, UCIe chiplets are finding wide deployment, and this is resulting in doing, and of course, we have done a good job in terms of, we talked about with UCIe 2.0, a lot of the manageability enhancements and all of that. So, but manageability and interoperability, they're becoming increasingly important. So to help with that even more, we are introducing 5 new features that are listed here, and I'm going to go through them one by one. Well, it's no secret that modern chiplets, they require firmware to function properly. This is to support external interfaces, internal structures, management features, right? A whole host of things that firmware does. And what we want to do is we want to avoid the need for each chiplet to have its own EEPROM or its own external flash, those kind of things. It helps, of course, with the system design because you're not interfacing to multiple ones, one for every chiplet, and also it reduces the costs. So what UCIe 3.0 did was we introduced a simple register-based mechanism for firmware download, which can be used via the sideband or even the main band, the UCIe, and can be implemented with a simple hardware finite state meshing. Now, here is an overview of the flow and the thinking. You have, this is your SIP here. This is the director chiplet. It connects to the flash. And this one manages the firmware. The director manages the firmware update within the SIP or the system in the package. By it loads the mutable firmware from the flash. It initializes the sideband network across the SIP, and then it facilitates the subsequent download of that firmware into the individual chiplets, which can then boot using the downloaded firmware. Now, chiplets can boot using that firmware through the director chiplet, and they can also subsequently request further firmware updates either through the sideband links that you see here or the main band through the director chiplet. And we have provision for existing protocols like MCTP, which is the Management Component Transport Protocol, and the PLDM, Platform Level Data Model. So you can use that and do further upgrades for firmware downloads. To ensure seamless interoperability between chiplets, we have defined data structures like circular buffers that allows for efficient communication and coordination for these firmware download within the SIP, right? So that's one thing that we have done. Second aspect is effective utilization of the sideband, right, is becoming critical while ensuring quality of service, which will result in, of course, greater customer experience in the long run. Now, to this end, what we did is we defined a mechanism for prioritization of events and pause resume of low priority bulk management traffic. Now, with management traffic, for example, or if you're doing a stream of debug data that you are dumping, those can go on and on and on for a really long time, right? They can go for like seconds, especially if you're doing something like, hey, I want to debug something, right? Those data is going on through the sideband. Now, in the presence of those kind of bulk traffic, there are certain events like, power down, whether it is power wake up, or, you want some low latency telemetry data, you want to switch to a redundant power supply, you want some kind of high priority, effectively some kind of high priority notification over the bulk traffic, right? Like debug dump or firmware download kind of thing. You should be able to interrupt that traffic, pause it, and then resume it back, right? And we are providing that capability with UCIe 3.0. The goal is the upper bound needs to be, somewhere around 60 nanoseconds, and we'll explain how we get there in a bit. But this is an example. The bulk traffic is going on here. Let's say somewhere over here, you decide that, hey, I have this high priority traffic that we are indicating as PT. So you wait for the next 8 UI aligned boundary. You pull the sideband clock low for 8 UI. So that is an indication to the other side that the next traffic is not related to this traffic. The next traffic is a priority traffic, and then you send the priority traffic, which is basically defined to be 32 bits. And then after that, you can resume back your normal traffic from NT8 onwards, right? So that's the basic idea. You can also have actually two back-to-back priority traffic. The 32 UI in the priority traffic is 23 bits for the priority vector, 5 bits for opcode, 3 reserved bits, 1 bit for parity. And the maximum switching time, as you can see, is that when you decide that you need to send a priority traffic. So I moved on. Okay. Sorry about that. So let's say if you decide here, it still takes a few, you have to wait till the next 8 UI boundary. So that's why this is the upper bound is 8 UI, and then the 8 UI to switch over there, and then 32 UI to transfer. So 48 UI roughly, and that's about 16 nanoseconds if you do the math with 800 megahertz clock. So that's that. Now, as I talked about it before with UCIe 2.0, we introduced the notion of a UCIe sideband only link for the UCIe standard package, and this that was there as a dedicated port for things like manageability, debug, test, all of that functionality. And the usage model is an anchor chiplet or a director chiplet that can connect to multiple chiplets and can form a ring using this sideband link. So that way your normal traffic in an ideal case doesn't get impacted by this management traffic. Now with UCIe 3.0, what we are doing is we are extending that sideband channel. Instead of forming a ring, we are going to support, if somebody wants, we can support a star topology. So with the star topology, you can minimize the hops because the director chiplet or the anchor chiplet is connected to every other chiplet. It has the benefit of getting higher bandwidth, lower latency, and of course, better security characteristics because you are not going through other chiplets. So, especially with complex systems, this is very valuable. And the question then is that, 25 millimeter is a restriction, especially with large packages. So we extended that reach to 100 millimeter. And it was easy because this sideband link is not running at 64 gig, for example. It's running at 800 megahertz. So it's the same. It's basically the same kind of channel, but it's only running at 800 megahertz. So it's easy to provide that extended reach. So what we did was we specified a few sets of parameters like input high voltage, low voltage, those kind of things, and what kind of resistance, driver resistance you need, all of those things, and that will ensure reliable operation over 100 millimeter, and that enables star topology, which is very important. Now, if you recall a couple of slides back, we talked about high priority events like power down, power wake up, fast telemetry data that needed to pause and resume bulk traffic. Now, there is another category of really critical events that can't even wait for that 60 nanoseconds upper bound that we talked about. Things like I need to shut down something in an emergency. I need to do a fast throttle because there is a thermal emergency going on, right? So this is like almost instant notification is what you need. And these are unplanned critical events. So they require SIP-wide simultaneous broadcast to all the chiplets. So with 3.0, we introduced open drain pins for low latency bidirectional events for these kind of emergency things. There are two categories that are defined, and we'll talk about that in the next slide. Now, these are not part of the UCIe link. They're not in the main band. They're not in the side band. They're defined by UCIe so that multiple chiplets just have the same mechanism across all the vendors and they will interoperate. So you're not going to find that in the pin map of the standard UCIe bump map, right? You provide it wherever you do because it's just two of them for your entire chiplet. So it's the same two pins. It doesn't matter whether you deploy 100 UCIe-S links or UCIe-A links or 3D links, or you deploy 5 of them, right? You still have the same two bumps, okay? And these pins are intended for package level routing, and they provide for a reliable and efficient means of communication across the chip, across the SIP, that is. And you will see that in the picture here, there are 16 chiplets, and they are basically connected with all of them, right? And then eventually they will be connected possibly at a platform level. Now, continuing on from the previous slide, in the system in package designs, especially when you have multiple chiplets from different vendors, managing the things like thermal limits, it's a complex challenge because you are using different technology nodes. They have different temperature reliability limits for each chiplet. And each chiplet has its own temperature sensing capability. They have their own associated error margins. So there is a different sets of maximum junction temperature is what you are going to get, TJ limit. And if you exceed the TJ limit, your transistor function is compromised. Now, to prevent exceeding these limits, if you need some effective mitigation mechanisms at the SIP level, both reactive and proactive. And this is needed so that you can maintain safe operating temperatures at the SIP level as well as at the platform level. So we need a standardized approach for those kind of things, and that's what we provided with UCIe 3.0. There are two key mechanisms. One is fast throttle, and the other one is emergency shutdown. Now, fast throttle is implemented by introducing a common dedicated open drain bidirectional pin, the type that we talked about in the last slide. And this is for all the chiplets in a thermal zone in the package. And this setup allows any chiplet to assert the pin when its internal fail-safe temperature limit is reached, or when it is signaled by an external platform that is experiencing very high temperature. And once you assert it, all the participating chiplets will throttle down their operations to a pre-negotiated level at a defined rate. And effectively that reduces the heat generation and maintain things safely. So again, those are shown in the picture over here. You can look at it. The second aspect is emergency shutdown, right? So again, same kind of a open drain pin. And when a chiplet's maximum temperature limit is exceeded, you might assert that pin, and that might cause emergency shutdown of both internal and external power sources. And this is a coordinated response, right? So that's basically what we provide here with UCIe. So two of these things that are using the open drain pins, fast throttle and emergency shutdown. UCIe's usage model, like we talked about, is constructing an SoC at a package level, or to bring the system from the board level to the package level, right? That's what you see in the picture here. You have things like processing dies that are possibly in the most advanced node, mix of accelerators, advanced node, established node, depending on the type of accelerator, memory and IO controller, which can be in a prior gen process, of course, on-package memory, analog chiplets, they're all connected through UCIe, either planar, 2D, 2.5D, or vertical, right? Doesn't matter. You can have them, mix of them. And if a customer wants a different mix, they can mix different chiplets, different numbers of, or different types of general purpose processor, accelerators, all of that, and they can get whatever they want. And that's basically what we have talked about, right? It is that we want to span the entire compute continuum from handheld through servers, through AI usage, and so on and so forth. UCIe retimers that we saw here, it's a novel concept that we introduced with UCIe 1.0, and it helps with off-package communication. So if you look at the picture here, you got your UCIe-based retimer, you get an optical connect, and it can basically, that's where it goes over and can come to a central entity where you might have a set of pool or shared memory, pooled accelerators, those kind of things. And with this, what happens is that you can realize the vision that you have a set of compute, a set of memory, a set of network acceleration on all of those kind of things, and you can compose the system dynamically, right? And that's basically what UCIe enables us to do. At a rack level or even at a pod level, right? So that's the unique thing with the UCIe, and it doesn't need to be optical. It can be some other kind of alternate media also, but optical seems to be what a lot of people are very interested in. UCIe offers the best metrics to meet the projected compute demand for the next 5 to 6 years. Now, even then, as you can see, we are not resting on our laurels. We are actively working towards making this even better. We are sensing what is needed, and we are acting based on that, right? And this is this table summarizes our KPIs, our key performance indicators. So you have 3 columns here: UCIe-S, which is the 2D, UCIe-A, which is the 2.5D, and UCIe 3D, which is the 3D interconnect, which is the vertical chiplets. Now for planar, these two are the planar, 2D, 2.5D. Now here we support multiple data rates, as you can see here, 4 gig through 64 gig. If you support a data rate, you must support all the lower data rates for interrupt. For vertical, again, just the SoC frequency, less than or equal to 4 gig. Each cluster is 16 bits wide for standard, 64 bits wide for advanced, 80 bits wide for 3D. A UCIe link comprises of 1, 2, or 4 clusters for planar. For vertical, it is just a 80-bit entity. And of course, you can have multiple UCIe links between 2 chiplets. We support, as we have talked about, a wide range of bump pitches. For 2D, it is 100 to 130 micron. For 2.5D, it is 25 to 55 micron. And for 3D, it is 9 micron down to 1 micron, right? So that's the third row over here. And then this is the channel reach, 25 millimeter, 2 millimeter. And for 3D, it is practically 0. Now, if you look into the metrics, this is the bandwidth density, bandwidth per source line, and then the bandwidth density as in over the area. So you get a range for 2D, 2.5D, and that range depends on the operating frequency. So if we take at this, for example, over here, you get 188 gigabytes per second per square millimeter at 4 gig. You will get 376 gigabytes per second per square millimeter at 8 gig. You will get 1646 gigabytes per second per square millimeter at 64 gig. You will notice that for UCIe 3D, the source line bandwidth density is NA. Now, we don't consume any source line. So instead of saying, hey, you divide a number by 0 and you get infinite, we just say NA. Now, the impressive number here is the bandwidth density, which is the area. And, look at these numbers. We start at 4 terabytes per second per square millimeter, and we go all the way up to 300 terabytes per second per square millimeter. And this is after taking out the overhead like VSS ground, all of that. And by the way, for these, the numbers, the 2D, 2.5D, the numbers are at 45 micron and 110 micron for the standard package. So, and you have room to grow, because if you reduce the bump pitches, these numbers will go up. So for instance, if you go from 45 micron to 25 micron, your bandwidth density will go up by 3.24x, right? So with 3D, of course, we get practically, infinite bandwidth. This is like, just to compare, external interconnect, the bandwidth density is in the double digit number. So even with 2D, 2.5D planar interconnect, you get 1 to 2 orders of magnitude better bandwidth density. And here you get 2 to 3 orders of magnitude more bandwidth density than the UCIe-A. And then the power number wise, the numbers are 0.5, 0.25 picojoule per bit. And these are an order of magnitude better than external interconnects like PCIe Ethernet, where you get about 5 picojoule per bit. Now the vertical numbers are what is really impressive. You are coming from 0.05 to 0.01 picojoule per bit, which is orders of magnitude better than even your planar interconnect on the package. So that's very promising. And again, this is because we have reduced the frequency and all of that. So this is like an architecture that is really well done by us. You also have very low entry and exit latency to the low power states. You can see 0.5, 0.1, and 1 nanosecond numbers. And vertical, you can turn on and off instantaneously. And in the process, you save 85% of power. Now, what this results in is linear power consumption with bandwidth usage. In other words, if I need 10% bandwidth of the peak bandwidth, I should ideally consume 10% of the max power, right? And this gets you closer to that. Now contrast that to external interconnects, where exit from this low power state takes several microseconds because the circuits are so complex. Now our reliability is very high, as you can see. The numbers are about 10 to the power minus 10. And as I said, in the case of 64 gig, you will probably end up with somewhere around 10 to the power minus 7, right? Anything less than 1 is acceptable. So clearly, these are very, very, very good numbers, and we continue to deliver power efficient performance. So let me summarize by saying that 3.0, it represents a transformative advancement in chiplet interconnect technology. It's the beginning of a journey, right? We are in the early phases of a multi-decade journey. As the semiconductor industry will continue to evolve, UCIe we will evolve and we will play a pivotal role, and we will enable the next generation of chip designs across the whole compute continuum. We'll provide the necessary infrastructure, will support the ever-growing demands of the modern computing applications. And of course, you can read through the rest of this, but please join us if you have not done so. With that, we have some time for questions. Samantha, let's see what questions we got, and anything that we run out of time, we will answer them as a blog. So please keep the questions coming.
Yeah, just to reiterate, we've received quite a few questions. So any we don't address today, we will address in a blog on the UCIe Consortium website. First question we have here, Debendra, is why do you not double the frequency in UCIe 3D for bandwidth density improvement like you did for UCIe-S and UCIe-A?
Okay. Uh, so short answer is that we don't have a shoreline constraint in UCIe 3D. As you noticed in the picture that we connected them in place, right? So that's point one, right? So most of these things that we are doing in UCIe-S and UCIe-A is because we are shoreline constrained. And yes, we can reduce the bump pitch, but the bump pitches are not reducing fast enough with the demand. So we increase the frequency to meet the demand. Now, if you look into the 3D, my range is 4 to 300 terabytes per second per square millimeters area, and that's a lot of bandwidth. So there we really want to be low frequency. As I said, right, even for planar, ideally we should be reducing the bump pitches and delivering the bandwidth. That's the better way to do that because you get an exponential increase. As I said, going from let's say 45 micron to 25 micron increases your number of wires by 3.24x. And of course, if we get to increase the frequency by still staying within the power profile, which is what we did, we will do that. So it's an engineering judgment there, but 3D doesn't make sense for us to increase the bandwidth because I want to be bump limited, and I'm not against I'm not up against any kind of first of all, there is no source line there, and I'm not up against any kind of a area constraint there either. So that's the reason why we don't increase the frequency in 3D.
All right, next question we have here is how do you know what frequency to operate at for the continuous transmission application?
Good question. It actually depends on the application, right? For example, in the picture, it depends on what frequency the DSP is operating at. And so you know that during the design team, as a SIP designer, you know what it is that you're putting together, and accordingly, you can choose the appropriate reference clock frequency.
All right, next question here. What is the difference between bandwidth shoreline and bandwidth density?
So the bandwidth shoreline is it's a linear thing, right? So it is gigabytes per second per millimeter, and bandwidth density is the aerial thing. So linear is like you're considering only one dimension, right? I can always go really deep and get a higher bandwidth shoreline number, okay? Because I'm reducing think of it as there is an X and a Y, right? So the bandwidth shoreline is the X component, how much bandwidth I'm getting on the shoreline. And then the bandwidth density you also need to look at is how much am I protruding inside the chip to deliver that, right? So that's the area consideration.
Alrighty, I think we have time for one more question here. We'll answer any remaining questions on our Q&A blog. The last question we have here is how do some of the planar concepts like a director chiplet talking to other chiplets to open drain pins work in the context of vertical chiplets connected through UCIe 3D?
So the director chiplet is connecting. Okay, I get it. So the question is the director chiplet is connected using planar, and how do you talk to the 3D, the ones that
Correct.
are up there, right? You can shoot an arrow up, right, so to speak. Okay, so a good question. Now the star topology that I talked about, obviously it cannot go from a director chiplet to another chiplet that is, let's say, 4 chiplets above the bottom chiplet, right? So you can't like put a ladder, so to speak, right, in here. The idea is in planar, you have a star topology, open drain and all of that. So the chiplet is think of the chiplets in the ground floor. Let's call it X. Now, if the X connects to the director chiplet using planar. Now, if X wants to talk to its chiplets on the upper floor, so to speak, on the vertical, then it does that through the UCIe 3D links, or you can do like a VR, something like that, like in the case of an open drain, and talk to them. But yes, good question. But there is no technology available where I can make a connection from a ground chiplet on one side to a something that is sitting on the fourth floor on the other chiplet. Maybe when the technology comes, we will address that. But yeah, good question there. You basically have to go through the ground chiplet on your stack, and then from there you have to go up, and that provision exists already.
All right, I think that is going to be it for today's Q&A session. Again, thank you all for the questions that we've received from everyone. We will be answering these via our blog. In the future, you can keep an eye out for that on the UCIe Consortium website. All slides will be available on the UCIe Consortium website as well as the recording. Thank you all for attending.